Alright, so let's first review what we did last week, okay, what you guys did in the lab. So the first thing we did was subject bromooctane to either a solution of KCl, potassium chloride, or a solution of Ki, potassium iodide. Okay, you had to choose which solution or which salt solution you were going to use. Okay, you subjected this, you started to let it heat for about an hour. Meanwhile, you did this reaction, okay? You put ammonium chloride and ammonium bromide in with some acid, transferred it to a step funnel, and then you added your 2-methyl-2-butanol, okay? So while this reaction was going, you did this guy, you separated it, and then when you were done with this, you went back and worked this guy up, okay? And do you remember what kind of sample you prepared at the end of this reaction? Was it a GCMS or an NMR sample? For this one, it was a GCMS sample. Okay, so we analyzed this one by GCMS, and this reaction, right, this is the one you prepared an NMR tube for. Okay, so this is the one we subjected, or we looked at by NMR. Okay, so we're going to talk about both of these instruments briefly today, and we're going to do them one at a time. Okay, so first up, this one, the bromooctane reaction. Okay, this one took the longest time. So this bromooctane reaction, do we think it is an SN1 or an SN2 reaction? Let's think about this. Our halide here, our leaving group, what degree is it? This is a primary leaving group. Okay. Well, are we going to form a primary carbocation in solution? Probably not. And so instead, we know that primary leaving groups are very fast in what kind of reaction? The SN2 reaction. Right? The name of this lab is competitive nucleophiles. We're just talking about nucleophilic substitution reactions, okay? So if these are SN2 reactions, can you guess what this one probably is? This is probably an SN1. We'll get there when we get there. All right, so our SN2 reaction. Remember the mechanism, right? KCl just looks like this. And so we just do a backside attack and we kick off that bromide, okay? Same with the iodide, backside attack. All one step, right? SN2, all one step. So we're going to have this guy. We probably also have some bromide in solution. Bromide with that leftover potassium. Okay. What else could be in our reaction flask at the end of the reaction? Okay. Before you worked it up, what else could be there? Let's think about what else could be then in our GCMS sample. Okay. That's what I'm talking about. What could be in our GCMS sample? We could definitely have product, obviously. Could we have some unreacted or leftover starting material? We did use excess of this guy, but maybe we have some unreacted starting material. It's definitely possible. Okay, we did subject these reactions to some phase transfer catalyst. Some phase transfer catalyst was in those reactions. And could we have unreacted KCl? So let's think about this. At the end of our reaction, we did an aqueous workup, which means we put all of our organic stuff in with an aqueous layer as well. And so is KCl aqueous soluble? Yes, it is. Is our phase transfer catalyst aqueous soluble? Yes, at least partially. That's why it's a phase transfer catalyst, okay? So I would not expect these guys to be in our GCMS sample, okay? Because they would have been washed away with our aqueous. Washed away in aqueous layer. Remember, you guys did this. You put this in a separatory funnel, you added some water, and then you separated the organic stuff from the aqueous stuff. Okay, so I would expect all of these things to kind of go away with the aqueous layer. So maybe all that would be left in our possible GMS sample, in our sample, would possibly be the organics. Okay, and so same with the iodide. Okay, again, all this would go away with the aqueous, same with our KBr that we made, but we could still have some unreacted starting material. We could. Okay, because again, this is a nucleophile, just maybe it didn't react with all of the bromide. Sure, that's definitely possible. Okay, so again, we subjected this to GCMS, so we have to learn about GCMS. Okay, GCMS stands for gas chromatography. Okay, mass spectrometry. Spectrometry. Okay, so we have to learn about the GCMS first. First up, the mass spec part. Okay, so mass spec is a little bit complicated, okay? So in mass spec, we take our molecules and we bombard them with a bunch of electrons. Okay, let me show you what it looks like. Here we go. Okay, here's our electron beam. Okay, our sample will be right in here. Okay, so we ionize our sample and we subject it to a big old bunch of electrons. Okay, so when we bombard our sample, our molecule with a bunch of electrons, what can happen is that electron can pop out one of the electrons from our molecule. Okay, it just literally pops out an electron. So now we have paired electrons, and then we now have one unpaired electron. So that's why it's a radical in our molecule. Okay, and we lost one electron, therefore we now have a formal positive charge with our molecule. So this is our radical cation. Okay, and this is actually what we're going to be studying. Okay, this is what gets detected. If I can spell detected, detected by mass spec. Okay, it's this charged cation. Okay, so here's an example here from your book. We just subject methane, again, to a beam of electrons, and what happens is that it pops out this one electron, gets popped out. So now we have two electrons, and this electron is now gone. Okay, so it's an unpaired electron, and it's got a formal positive charge on the methane, okay, on the carbon. So we have formal positive charge, and again, this is what gets detected by mass spec. Okay, so the cool thing is then what we detect by mass spec is its mass. Okay, detect the mass. Wow, I cannot write. Detect the mass by mass spec. Okay, so how this works, again, what happens is that after we bombard our sample with electrons, okay, we bend it around this tube, okay, and it separates ions based on their mass. Okay, so ions that are too light bend a little bit too much and they come out and they hit the wall. Bends that are too heavy, they don't bend very much, and they come around, and pretty much the ions that we want, okay, so we can change this kind of slit, or we can change the range of masses that we're looking at, but only the ions of the right mass make it around that bend, and we can change the range of masses by changing the magnetic field. And we detect the ions that we want, okay? So then we get little peaks like this that correspond again to different masses, okay? Peaks correspond to ions of different masses, okay? So again, we are detecting things based on their mass, okay? That's how we are detecting things. Again, it's mass spectrometry. And we make these things, again, by bombarding them with electrons and making these ions, okay? So we bombard with electrons, we get this charged cation, and this is what we detect. We detect the weight of it, the mass of it, okay? So the thing with mass spec is when you hit something with a bunch of electrons, a bunch of different things can happen. Not to mention we have these very reactive radicals, okay? So different things can happen. So for instance, if we take ethane, and again, we slam a bunch of electrons to it, okay, we can get our radical cation. So this is again just one of those electrons, and this CH bond has been popped out. So we have an unpaired electron and then our formal cation. Okay, this is known as the molecular ion because it has the mass of the original compound. Okay, right? It's got 2 carbons, each 12, so 24, plus 6 H's, 30. Okay, M over Z, this is the mass. Okay, this is the mass to charge ratio. And all it's really saying is the mass. Okay, because the charge is always +1, because we have a carbocation, sorry, not a carbocation, we have a cation. So it's always +1, so it's pretty much just the mass. Okay, but we report it as M over Z. And again, this is our molecular ion, and this is the thing that we are often looking for. Okay, so we care about the molecular ion, because again, it has the mass, the same mass as our original compound. Okay, so that's the molecular ion. It has the same mass as our original compound. Okay, but like I just said though, when we bombard our sample with a bunch of electrons, a bunch of different things can happen. Okay, so for instance, we can have our nice radical cation where again we have popped out one of the electrons from this bond here, okay? But then if we can imagine this reacting further, this radical, this bond, I guess, kind of, which only has a really like a bond order of 1/2, can actually break, and so we can have our hydrogen radical and be left with a carbocation. And so this has a different molecular weight, actually, and so this would be another peak in our spectrum, okay? But another thing that could happen, like why only pop out an electron from this bond? Why can't we pop out an electron from this bond? Sure, that can also happen, okay? We can also break this bond in doing so, kind of like we did here, okay? So in our bombardment of electrons, we can liberate one of these electrons, so we get 2 electrons out of there, and then the radical leaves with the carbon. So we could have this radical and then leave a formal carbocation behind, and again this has a different mass now, okay? It's only got 1 carbon and then 3 hydrogens, so 1 carbon is a mass of 12 plus 3 hydrogens 15, okay? And again we report the M over Z, but Z is always +1, and so this is what we would detect by the mass spec, and so again this would correspond to another peak, okay? We can't detect the radicals because again they don't have a charge, okay? It does have to have a charge for us to detect by mass spec, okay? And again, all of these compounds then that have a different mass are going to be different peaks in our spectrum.